Okay, great. Thank you all so much for having me. This is really fun. I think I've met most of you, but I'll just introduce myself again. I'm Pamela, in case you haven't met me, Douglas. And you've heard a lot of lectures on machine learning so far, so by the end of this course, you all are going to be experts in machine learning algorithms and everything decoding related to fMRI and neuroimaging. So I'm just going to kind of expand upon a lot of the things that Jesse Rissman talked about and kind of build on that and recapitulate a lot of the things that he said, because sometimes it's nice to hear things a couple of times from a couple of different perspectives. So first we'll start off just talking a little bit about what do weight vectors mean, and I'm specifically going to talk how they relate to SVM, because support vector machines are kind of the most popular and used most commonly in fMRI decoding. And then I'm going to talk about something that's slightly controversial. Feature selection, is it important? Again, Jesse did introduce this topic, so I'm not going to go through the basics again, but I'll talk about a few of the issues that are kind of interesting related to feature selection. And then I'm going to talk a little bit about what can you do beyond support vector machine. And then lastly, I'll give this plug for this amazing toolbox that comes out of New Zealand, some of my colleagues in New Zealand, and they're a lot of fun. Okay, so weight vectors and SVM. So first, you've heard a lot about, at this point, voxel-based encoding models and also decoding models. And so at this point, you're all well versed in knowing that encoding models are kind of asking how activity varies when there are changes in the outside world, and conversely, decoding are asking more, what can we learn about the outside world by observing activity? These are kind of the conventional ways of thinking about encoding and decoding, and they're both essentially ways of mapping data to either the experimental manipulation or the stimulus. So early on, one of the motivations for running decoding models was this idea that we might be able to learn more about patchy functional segregation in the brain. So of course, decoding is inherently multivariate, so the idea was that we might be able to analyze these patterns and be able to learn more knowledge. So Jesse's gone through this quite a bit, but I'll just mention that again. So again, why should we use decoding? The idea is that traditional mass univariate modeling might be limited, and that information might exist in distributed patterns. And MVPA and also just decoding methods may therefore be useful for examining this distributed coding. And so this is from Etzel, 2013, and this is just showing the number of publications that are related to decoding that have increased over the years. And this is kind of similar to the slide that Russ Poldrak showed, showing that we've just really expanded the number of publications related to fMRI over the past few decades. But we've also been publishing a lot in the field at this convergence of machine learning and neuroimaging. So that's kind of an interesting trend. So there's obviously a lot more Haxby references, Krieger-Scores references that have been taking place over the past few years. So what can we do with decoding? Most people want to do stimulus decoding by response pattern classification, which was that first mapping that I showed you. Which stimulus items elicit patterns that are distinguishable? That's perhaps a question that you're trying to ask, because at the level of voxels, the resolution of a voxel, can we actually distinguish between different patterns? If you can't, then maybe your decoding is kind of a trivial thing. Even if you're trying to predict brain patterns, which I'll mention later, if they're so similar, it might actually be fairly trivial. You could also ask, which items does a region treat as identical and which does it treat as distinct? So that's kind of another way of reframing that same question. But more traditionally, kind of prior to fMRI, two of the things that were commonly asked in the machine learning community with, say, EEG data or maybe just structural MRI data were, can we predict group membership? So can we do computer-aided diagnostics, for example? Or can we do brain-machine interfaces? Can we use EEG, say, to control robotic arms? I saw a really interesting presentation once from a group in Japan that had built an entire apartment, actually, for people that were locked in. And so they had people using EEG to control everything from moving around a wheelchair to changing the television channels to turning the lights on and off. It was actually completely amazing. But what's also amazing is that the volunteers, who were people like us volunteering in this experiment, all threw up their hands and just couldn't take it after, a couple of hours, sometimes a day, just because it's really frustrating if it's not working and you're really trying to move the wheelchair, and just so it's really challenging, brain-machine interfaces, brain-computer interfaces, in part because the brain is, of course, non-stationary. So a couple of years ago, Klaus Robert Müller came here and spoke about brain-computer interfaces, and that was a really fascinating talk on how we can deal with the fact that the brain is always remapping itself. You might recall, if you've read some of these early papers on brain-computer interfaces, even when primates are used, usually you have to retrain the neural network, or if you're using a neural network or any type of classifier each day, because overnight, even in the motor cortex, there's a lot of remapping and a lot of non-stationarities that happen. So by now you all know this. What is machine learning? It's a branch of artificial intelligence that takes in data and tries to learn and make predictions. But there's really two main classes. There's supervised, where we know the label on some training data, and then we apply that to some test data. But there's also unsupervised. This seems to receive, I think, less attention in our field, but it is also really fascinating. I've done some work with Ariana Anderson here at UCLA recently, using unsupervised non-negative matrix factorization to try and understand the dimensions of ADHD, because it's a very difficult disease to try and categorize into its different presentations, since hyperactivity and impulsivity and inattention seem to kind of overlap and span, and it's hard to label a specific patient as ADHD with an inattentive subtype, or now they're called presentations. So that is kind of an interesting aspect of unsupervised machine learning. So what do machine learning classifiers operate on? They operate on features, which are descriptive variable categories. Most of the time in this course, we've been talking about using voxels, say, as our features, but you can also have things like gender, male, female, IQ. You can have all kinds of different categorical variables. You can have missing data. So it's not just numerical values of voxels. There's a number of different attributes or features. These two words are used fairly interchangeably in the machine learning literature to try and make predictions. So here's a few examples of some common features that are used in decoding. Voxels, as we've talked about. Searchlights, which are really nice in the sense that they try to reduce local redundancy, which we know to be the case in a lot of fMRI measurements. There's also classification based on functional connectivity matrices. You can also use graph theoretic metrics as features if you like. I've seen some papers using effective connectivity, DCM parameters, to make predictions and diagnostic categorizations, and also independent components. So just to summarize the analysis flow, we have an input space, say some voxels. We map that to a feature space. We then perform a classification, and then we have this output, which is a % accuracy of how well we were able to make predictions on the test set, as well as these feature weights. And these feature weights can be mapped back to the brain, but that's what I'm going to talk about, is should we really be doing that? Why or why not? So one thing to think about, with each machine learning algorithm, there's an inductive bias. So machine learning is kind of an ill-posed problem. There's no one solution. So in order to constrain the problem, we have to make some assumptions, and this comes in the form of the inductive bias. So if you have this data, part of the inductive bias could be, do we want to try and separate it with a line? Do we want to use a curve? Would we like to use a higher order polynomial? How do we choose between these different inductive biases? So some inductive biases are parametric. So if you're doing Bayesian classification, you're assuming essentially that the distributions adhere to a Gaussian distribution, for example. But not all inductive biases make assumptions about the underlying distributions. So some of the assumptions could be just based on what type of discriminant or boundary is used to separate the different classes. So those are non-parametric. So most of what I've seen people apply in the fMRI world is non-parametric because most people are using linear discriminant or support vector machine. So by far the most common that I've seen applied is the linear support vector machine. This is useful because it is very computationally effective when you're dealing with high dimensional data, like with fMRI, in part because, as I said, it doesn't depend on characterizing the entire distributions, but rather just looking at the points which are close to the decision boundary, as we'll see. So with SVM, or any linear classifier, you first define the model. So in this case, X is the input, theta is the model parameters. And here the model parameters, W is the weight vector, and W naught is the threshold. So this model here is our inductive bias. The form of our model is the inductive bias that we're taking. From there, you define a loss function. Often this is just the difference between the desired output and the model approximation. And then in order to estimate these parameters, we have some sort of an optimization procedure. So this often happens where you initialize some random weights. Maybe they're not random, but sometimes they're random, the initialization. And then you perform some sort of optimization procedure to iteratively change the weights as well as the thresholds. And so an example of this would be gradient descent, where you take the gradient of the loss function or the cost function with respect to each parameter, and then you update or you change those parameters within a loop. Usually, it doesn't have to be a loop, but most often. In this case, if you're using gradient descent, you would update the parameters against the gradient. And finally, once you have your model tuned on your training data, you then apply the tuned model to the test data. So as I said, Jesse Rissman has talked about this quite a bit, but I'm going to try to provide a geometric description of what this really means. So it's easy to first think about the Fisher's linear discriminant analysis, or any LDA kind of procedure. So it's also easy to think about it in 2 dimensions, or 3, but I like to take the simplest case because I think it's the most clear, effective way to visualize things. It's hard to imagine n-dimensional space, so we'll start with 2. So in this case, we have stimulus class 1 and stimulus class 2. Each has their own distinctive means, and we're trying to find the weight vector as well as the threshold such that when the data are projected onto that weight vector, that the data can be maximally separated. And so here's an example of a very poor choice of a decision boundary as well as a W vector. If we choose this W vector here, when the data are projected, you really can't get much class discrimination here. So this is true for SVM as well as linear discriminant analysis. The big point here is to just note that this W vector is orthogonal to the decision boundary. So what happens is these points, you can think of it as though they're being projected onto the W vector, and then you later apply this decision boundary. So here's an example of a better choice for a decision boundary. So Fisher's linear discriminant and LDA are all really nicely described in a paper from Klaus Mueller's group by Lem. It's a neuroimage paper in 2011. So if you're interested in understanding the nuances of how these boundaries are chosen between the different LDA learning algorithms, then I highly recommend that paper. So with SVM, we're interested, again, with using the same model, but this time we're interested not just in separating the two classes, but finding the maximum margin hyperplane. So we're interested in separating the two classes some distance away, and we want to maximize that distance. So this is some math. If you don't like math, then don't worry about it. I heard someone once say, if you don't like it, you can just think about it as decoration. So if you're not into math, then maybe this is just decoration. But if you like it, then maybe you want to read the Vapnik and Cortez 1995 paper. There's a nice long appendix there. But as I said, we're interested in maximizing the distance between the points, and we want it to be some distance. So it's often useful to constrain the problem by setting the distance times the norm of the W vector equal to 1. And then it becomes a Lagrangian problem. So you might recall from your calculus that when you're trying to maximize or minimize a function with respect to another function, then you can use these Lagrange multipliers, and that's one way to solve this problem. But the interesting thing about this is that in this process, most of the data points don't have any influence on the selection of the decision boundary. And so most of them vanish. The ones that we're left with are the points, in an optimal case, not in the case where we have the soft margin, but in the optimal case, the points that we're left with are the points that lie along the decision boundaries. And those points are called the support vectors. So when calculating the actual W vector, it's useful to average across a number of these support vector points and their parameters just for numerical stability. So for that reason, that's why it's called a support vector machine, is because it's a machine, I guess, of all of these different points that are the support vectors. So the geometry of SVM is, again, very similar to the linear discriminant analysis, the LDA approach. We have two different classes. We have our W vector, which is orthogonal to the decision boundary. We're trying to maximize that boundary. And so here are those points that I was talking about, the ones that actually make an influence, which are the ones closest to the decision boundary, and those are the support vectors. So I guess I'll repeat this just one last time, just because now I'm about to explain why it's difficult to interpret the weight vector. But again, just note that this W vector is, again, orthogonal to the decision boundary. So this is a worst case scenario that was pointed out by Stefan Halfa in 2014. It was really also pointed out by Guyon and Iseloff in 2002, which is that interpreting these weight vectors doesn't really make sense. And so it's kind of worth spending a moment thinking about what this figure actually means. So this is, again, supposing that we have two different channels, x1 and x2. It's very clear here that x2, if you project the data onto x2, it really doesn't have any class-specific information. On the other hand, if you project the data down onto x1, it absolutely contains a lot of class-specific discriminatory information. But if you put these two in a classic LDA kind of scheme, what ends up happening is that the weight assigned to x2 is, in this particular example, is about twice that of x1. And so this is, again, kind of the worst case scenario, but it can happen that a channel or a voxel that has no information on its own is assigned a very strong weight. And part of that has to do with the covariance between the two. So if the two were orthogonal, then the covariance is 0, and this is not a problem. But it is a problem when there's shared information between the two. It can also be a problem when you have multiple voxels. One voxel that's a noise voxel can be given a very, very strong weight because it's essentially absorbing all of the noise across, that's shared across all of the different voxels. So this is an important point. So it's a little bit tricky, but if you do map your weight vector back onto the brain and you present it like this, even though you're not necessarily interpreting the weights, I think it can, on some level, be considered an implied interpretation because these sort of look like maybe the results you would get from a GLM analysis. But they're not. They're weights from a machine learning analysis. So what can we do with the weights to try and interpret them? Well, Stefan Haufe says that what we can do is take the weight vector and back project it into the original space. And so if you have a square matrix and a very simple problem and a linear classifier, that turns out to be the inverse transpose of the weight vector. So you can just take the weight vector, take the inverse transpose, and there you go. Then you can just show the weights if you want to. And there's nothing wrong with that, but there are some complications actually, because if you have a lot of redundancy, the weights that are assigned to the voxels that actually do contain a lot of information kind of fall off. And so with more redundancy, this becomes very problematic, and how do we interpret these weights? It also becomes more complicated when you have perhaps different kernels, as Jesse talked about. You can use radial basis functions or polynomial kernels. It becomes a little bit more tricky. Or with, say, neural nets, how do you get back to that original space? How do you make sense of those features? And how do you interpret them in the context of whatever cognitive process you're trying to probe with an experimental manipulation? So, yes. So this is kind of inspired by something that Russ Poldrack wrote in 2006. He talked about the dangers of reverse inference. So one of the dangers of reverse inference is looking at functional activation maps and making inferences that those have implications for cognitive processes, as opposed to just the experimental manipulation. So there's something similar with machine learning in the sense that we don't want to take the weights, as I've said, and project those back and then make inferences based on the weight maps. So be careful with what you say with your machine learning weights. So just to summarize this, the results should always be interpreted in the context of the inductive bias that you've used for your model. Decoding may also provide insight into the multivariate nature of neural code, but I'm not exactly sure how. That's still kind of an open question for me. And although it's tempting, the weights that are assigned to features of voxels should not be interpreted directly, unless they're independent. So that's something to consider. Okay, so now I'm going to talk about, now that we have our geometric interpretation of SVM and some classifiers, I'm going to talk about if feature selection is or is not important. So feature selection can be performed either as a separate step or alternatively as an internal step within a regularization scheme. So if it's performed as a separate step, there's a couple of different ways that this can take place. The first is maybe just a filtering approach, where you perhaps have all of your voxels and you're interested in just looking at, on the testing data, those voxels that have some certain z-score. Or alternatively, you could threshold just the ones that have more than a certain level of variance. So I think I saw this in one of the earlier papers on decoding fMRI. They just were interested in voxels that actually changed. So they had a variance threshold. So that's almost like a pre-processing step. You can also use wrapper methods. So an example of this is support vector machine recursive feature elimination. So in this case, what you do is you wrap the classification algorithm within a nested cross-validation, which I'll talk about. And you try and remove, sometimes one at a time, sometimes you randomly select groups, and you see what happens if you remove those. Does the error increase or decrease if you remove groups of features? And then there's also projection methods. There's you can use PCA or ICA to try and project clusters of features that are similar into a lower dimensional space. One that I really like recently that I'm still learning about is random projections. It turns out that this technique is not actually that random. It finds clusters that are really nicely separated. And clusters that are well separated on just a few data instances. So, for example, if you're trying to discriminate between tigers and hammers, it might be very, very different. And so you can group those and project all of those clusters down into smaller dimensions. So if you're not using feature selection as a separate step, you can also do feature selection in a way within a regularization scheme. So with regularization, you just modify your cost function. So you have the data misfit, but you also have some sort of regularization parameter that penalizes for complexity. So in this sense, the regularization is trying to move your model towards a more parsimonious model fit by penalizing the addition of extra parameters. So one example of an inherent regularization scheme is SVM. So support vector machine has this nice C parameter, which can be used to weight error in its estimation process. So when C is large, you tend towards the hard margin, and it penalizes error points more strongly. So this results in a smaller margin, and when you have a smaller margin, there's typically more support vectors. There's more points that are influencing the selection of the parameters. But one of the things that's kind of interesting is there's no one C parameter that universally fits the data, that universally fits all data. So this is a figure from Hasty, 2013. He shows that with different radial basis kernels, so the width, if you want to think of it that way, or the sphere, the size of the sphere, has different performances based on the C parameter. So in some cases, certain radial kernels would prefer to have more regularization, but then when you have smaller kernels, maybe less regularization is better. So there's multiple parameters and things that should all be tuned simultaneously, if that makes sense. And so radial basis functions, I just put this as an aside, the size of the kernel might be somewhat analogous to, say, the size of a searchlight radius. Okay, so coming back to this question, is feature selection important? There's this really interesting paper by Carlton Chu where he had the Adhd data, which was trying to predict MCI versus Alzheimer's disease, so mild cognitive impairment versus Alzheimer's disease, just using structural MRI data. And he tried out t-test filtering as well as support vector machine recursive feature elimination. So wrapping a support vector machine within that iterative loop that I spoke about. And he came to the conclusion that feature selection methods actually didn't improve accuracy unless you were using some sort of a priori knowledge, like say using just the voxels in the hippocampus or something along these lines for trying to predict Alzheimer's disease or not. There we go. But if you take a closer look at his data, I think it's actually kind of interesting. This black line here represents the classification accuracy if you're using all of the voxels in the brain. And these other curves represent the accuracy for different variations on the t-test filtering or the support vector machine recursive feature elimination. And so I find this interesting because he came to the conclusion that feature selection didn't really help because technically using all the voxels did overall achieve the best accuracy. But if you overlay a 95% confidence interval here, you'll see that these other approaches using, say, 6,000 voxels as opposed to maybe 100,000 performed almost as well and within the 95% confidence range. So this is kind of, to me, a little bit of a theoretical question. If you can perform almost as well using a small fraction of the features, should you choose that option, or should you go with something more complex using 100,000 voxels, say? I'm not sure, but I guess because I kind of come from the parsimony camp, that the Occam's razor approach is what you would choose. So you should choose the model that's more simple, that with trading off just a small little bit of loss in the prediction capability. But it also depends what your purpose is. If you're actually just trying to make this diagnostic prediction, maybe you really do care more about the accuracy, so you'd rather just have everything, all of the voxels in there. So this is another example, another thing that I participated in, which was the Adhd 200 machine learning competition. This relates to feature selection, and to me, an extremely frustrating way. So in 2012, there was this public release of about 1,000 different structural MRI, functional MRI, as well as gender, IQ, all of these different parameters. And the goal was to take this training data, and then to predict on 200 new subjects the ADHD diagnosis using these neuroimaging features. And so I was on the UCLA Yale team, and we placed third using tons and tons and tons of features. We started off with something like 100,000, more than 100,000, hundreds and hundreds of thousands of features, and we used SVM RFE, starting with all the features and kind of using a backward approach, trying to find the least amount of features that we needed. And we had resting state functional connectivity features, graph theoretic measures, ICAs, we had free surfer volumes, and it turns out that the winning team used only the demographic features. So this is extremely frustrating because they didn't use any neuroimaging features. So in theory, if your feature selection approach worked really, really well, if the only thing that was informative was gender and IQ and whether they were diagnosed in Beijing versus New York, then theoretically the feature selection algorithms should have just eliminated all of the brain data and found just those demographic features. But all of the teams that use neuroimaging features performed worse than the team that just used those demographic features. It still bothers me. I still haven't gotten over this. So I still talk about this because it still bothers me, and it really does, to me, still highlight why feature selection is definitely important. However you decide to implement it, it's definitely an important step, especially because as neuroimagers, we have such massive data. We really need to think about how to pare that down into something that's useful for prediction. Okay, so I've talked a little bit about these C hyperparameters, and maybe if you're using a kernel, maybe you have the width of your radial basis function. But how do we select these internal parameters given that we have a lot of different moving parts? Well, one way to do it is not just cross-validation, which you've already heard about from Jesse, but you can do something called nested cross-validation, which I mentioned earlier. So in this case, if you have a training set and then your out-of-sample test set, you break your training set further down into more training and testing sets, and you can loop through the training and test sets this way. So you can learn your hyperparameters, the parameters within your algorithm, using this nested approach, and then eventually apply it to the out-of-sample left-out test data. So this is just an example of how you can do different folds. So this is, I guess, a 2 by 3 or 3 by 2. I'm not sure exactly how you would call this, but this is where you have 3 and you kind of iterate the first 2, and at each point, different groups of the data become the left out test set. At some point, though, you might start to wonder, how do I know if I'm peaking? How do I know if maybe somehow in my code there was an error and it snuck in and I've accidentally been using some part of my training data on my test data with all of these different nested cross-validation. So some thoughts that come up, and this slide is from Nico Kriegeskorte, is some examples of ways that you might accidentally be doing this. The first here is that the same data is used for training and testing. Luckily, according to him, his subjective assessment is that this is very rare. But if you do this, then the severity is obviously quite bad if you're training and testing on the exact same data. If you have non-independent data used for training and testing, that's also fairly similar. This one here is a little bit tricky. So if all of your data is used to define an ROI, and then that ROI is then used as essentially as a feature selection approach, that's also peaking. If you set averages of analyzed data on the same data used for sorting voxels, that's also, I don't know, I think less common. And there's these couple others I'll let you read. But these are things to think about, different ways that your analyses can be circular. So you don't want to do that. So one of the things that I think is a good sanity check is to do a permutation test. So I have no idea why you would want to classify the difference between emus and pairs. But if you did, then maybe you would want to run a permutation test where you take the labels and you shuffle them at the beginning, and you hopefully get what you would expect chance to be. So if you're doing a binary task like this, and you shuffle the labels and then you get 90% accuracy, then there's probably something wrong with your process. If you shuffle the labels and get roughly what you would expect chance to be, then you're probably doing good. I've also do maybe 10,000 permutation distribution, a null distribution of what you would expect the chance to be. And so I've also seen some people use that null distribution in ways to extract p-values from classification tests. So that's also something that you can consider. Okay. So thinking a little bit beyond just SVM, why would we want to do that? So as I mentioned before, each classifier has its own inductive bias. And so there's also this amazing theory called the no free lunch theory, which is actually not true at NITP. We all have free lunch every single day here. So aside from NITP, there's this Wolpert and McGreedy theory, which says they proved that no one classifier universally works best across all domains. And so it's a good idea to test out different models. This is an example of this is an example that I actually have from a few years ago on some human decision-making data. And it actually turned out, this is the group level result. I compared K star, which is similar to K nearest neighbor, but it's more stochastic, naive Bayes, support vector machine, decision tree, Ada boost, and random forest, which is a way of bagging different decision trees. And it turned out that SVM performed the worst. Linear SVM performed the worst, even after tuning the C parameter. So SVM is not always going to work the best. So the data that I was speaking of actually came from Sam Harris in 2008. He had people make these categorical judgments on things like, I own a toaster oven, and then they would have to say yes or no, I don't own a toaster oven, or mathematical or religious statements. And so that data was trying to make predictions about his data, belief versus disbelief. So one of the things that I thought was kind of fun, just as an aside, is that the decision tree-based classifiers worked the best for modeling human decision making. So here's an example of one of the decision trees, and this was using ICA-based features. So here's an example of the overlap between the ICA-based features that were used in this particular decision tree with the general linear model results. So I'm not actually going to do a formal two truths and a lie like some of the other people have done, but if I were going to do two truths and a lie, one of them would definitely be related to this. This would be my outlandish truth that I would hope you would choose as the lie, but it was actually true. After doing this study on decision making in the brain and being able to predict not just mathematical but also religious belief versus disbelief, there's this guy named Harold Camping who came along, and he predicted that the rapture was going to take place on May 21st, 2011. I think there was another one in 2012 and another one later. And so this group of British documentary filmmakers decided to follow his followers, and they brought some of them to UCLA and asked us to see if we could make predictions about their belief system. And so this is a bizarre decision tree. Do you believe Harold Camping's right? No. Well, I guess that's the end of the decision tree. Yes. Well, then does the rapture happen? If it does, then if you're a Harold Camping follower, then I guess you're taken up into the sky. If not, then I knew of people in Los Angeles that were planning to go on a looting spree and steal lots of shake weights. So, so anyways, this is a ridiculous truth. This actually happened. I actually did scan the Harold Camping followers. Unfortunately, nobody was able to come back after the May 12th. I kept asking them, can I pencil you in? Oh, but I won't be here. So they weren't able to come back for the second brain scan. They didn't think they would be here, so it was, the scheduling was irrelevant. So another set of learning algorithms that are becoming quite popular is a lot of work from Nico Kriegeskorte on deep learning and neural nets. So neural nets can be shallow, they can have many hidden layers, they can have lots of nodes, they can be feed forward, feedback, they can be recurrent. The recurrent ones, some people say they argue that they're quite similar to Markov chains. So this is a whole other class of learning algorithms. Interestingly, a lot of the neural networks that I've seen have been winning the Kaggle machine learning contest lately, so it's worth noting that these machine learning algorithms do seem to do really well. And this is one of his results where they compared lots of different types of methods for estimating the machine learning algorithms, and these deep convolutional neural nets seem to, with many, many layers, seem to perform very well. But of course, there's this problem of what does this mean? How do we make sense of this how do we learn anything about neural computation from machine learning neural nets, which were in fact originally inspired by the architecture of the brain? Is there any way to map this back to something that can help inform our knowledge about cognitive processes? So one of the unfortunate things about both decision trees and neural nets is that if you give them both enough parameters, if you give enough splits for a decision tree or just enough hidden layers in a neural net, you can actually learn any training data perfectly. So unfortunately, what begins to happen is once you've learned that training data perfectly, at some point you stop learning the information and you start to train on the noise. So this is overfitting. And so with decision trees, there's these internal parameters, like I talked about, that can help you do things called pruning, where you start with, there's two ways to do it. You can start with nothing and build upwards, or you can start with building a decision tree that classifies perfectly on the training data, and then you knock out randomly different nodes and you see how the error changes. And you have different thresholds of error tolerance for keeping those nodes. There's similar things with neural nets. You can do all kinds of different things with adding new nodes or adding new layers, and there's things called weight decay and weight sharing that can help you figure out if you want to add a new node or a new layer. So if you want to build upwards or if you want to start with everything and move backwards. So I really like this Alpayden book on machine learning. It's really a nice introduction and it's very readable. He says that you should always start with something complex and then add complexity. So if you start with something small and add complexity, then you can see if that complexity is warranted. I think had I done with this with the ADHD 200 machine learning competition, maybe we would have done better because we would have perhaps started with all of the demographic features and then realized that by adding the neuroimaging data, we were not getting any more traction, rather than starting with all of the features and progressively eliminating them. So it's just something to consider. Do you start with everything and move backwards, or start small and add? So sometimes you end up with the same result, but sometimes you don't. So just to summarize, this is kind of bringing back this thought from Russ Poldrak's lecture, where he showed the number of publications increasing and asked, with more publications, will we learn more? If we continue on this same trend where brain imaging and machine learning are starting to converge, do you think that we'll learn more about neural computation from machine learning? I'm not sure. I think it's kind of an open question. Hopefully, yes. Another thing to think about is that each time we train a classifier, it's usually that we're giving subjects a particular task, and that's the training data. And the test data is also that same task, almost always. And so on some level, if you have a really complicated neural net that's learned really well on the training data, the test data probably has a lot of overlap and is very similar. So in theory, it's going to apply very, very well. But how well will that neural net that you've just trained work on a new task? So in that sense, we're feeding our classifiers with each experiment data that's biased towards that specific task. And so I kind of wonder how well we can actually learn about learning, how well models from different tasks can be applied to other tasks, and if there are sort of canonical learning motifs, if those can translate across tasks. So one of the things that I find interesting is in machine learning, they have this thing called domain adaptation, which is a way of reweighting your model to fit new data. And there's all different strategies for doing this. And I thought it was interesting. There's this fairly recent paper by this group, Anderson, where they essentially did do this. I don't recall that they used this term domain adaptation, but they did take new semantic words and try to predict the brain the patterns of activity for that particular word by using a reweighting strategy. But in order to do this, you have to have a really nice model of your stimulus. So you have to have a model of your stimulus and how that relates to the stimuli that the model has been exposed to. So thank you all very much. Just very quickly, I wanted to give a quick plug for this toolbox called Weka. It's my favorite machine learning toolbox. It has a really cute bird that cannot fly, but it tries really hard to fly while you're classifying. And there's all of these lectures from this group. They have a Coursera and an MIT edX. So there's this amazing group of New Zealanders. They're funded by Google, and they have this repository of machine learning algorithms. They have tons and tons and tons of feature selection techniques, tons of dimension reduction, every algorithm you can think of, support vectors, tons of neural nets. It's huge amounts of decision trees. It's really amazing, and they have a really nice procedure for vetting the algorithms before they get added to the repository. So the machine learning community kind of vets the algorithm for a while before it eventually gets added. Doing things like nested cross-validation, it's just a simple flag. So a lot of these these optimization procedures are really easy. And I worked with them over the past year, and finally now you can add your NIFT data directly to WECA, so now there's this brain imaging toolbox. And I've demoed WECA in past years here at NITP, so if you're curious about how it works on just simple data, you can try out some of those demos and see the really cute WECA bird fly around. And if you're interested in learning more about the brain imaging toolbox, there's a whole set of lectures that are free online. So, thank you.
I'll actually go ahead and relink Pamela's demos to our schedule for this year so you can see those. WECA is fun, and WECA is it's distinctly usable in ways that the MATLAB-based ones are distinctly difficult. Questions for Pamela?
Thank you very much for the great talk, Pamela. ADHD result that you weren't too happy with. I was just wondering, could that be due to the fact that the diagnosis to begin with is made mainly based on behavioral and observational data, so that actually performs a lot better, but once you bring in the brain imaging more biological data, it doesn't classify as well, because what we consider ground truth is based on something else. But in addition to that, could there be other subpopulations of ADHD patients that we're not really aware of, because again, we're classifying based on behavioral data, not necessarily from the imaging side of things?
Yes.
It's more of a comment as opposed to a question.
Yes, yes, I completely agree. And so that's partly why I started to become interested in what the underlying dimensions of ADHD were. And so that's why I worked on this non-negative matrix factorization paper with Ariana Anderson, who she'll be speaking tomorrow, to try and understand exactly how many different inherent groups there were within the ADHD population based on the brain data. So we were curious if the brain data supported the fact that there were, say, 3 different presentations of ADHD. And it's difficult because, as you're saying, we don't really have a ground truth. So sometimes you can take these clusters that you find and see how the classification accuracy changes if you have more or less. Otherwise, you just have penalties for the number of clusters that you find. We found 6, for example, seemed to be a nice number, but there was more information if you had more different groups. So, yeah. So the question of whether ADHD is dimensional versus taxonomic is, we decided it was more dimensional based on this particular data, but it is very hard. Where do you draw the lines? And should those lines be drawn at all? I don't know. So at least between the different presentations, it's difficult.
So what is the data size of that computation data set?
What was the data size?
Yeah, so how?
I think, well, it was 973, I think, in total. 200 of those were the left out sample. For each subject, we were given resting state, fMRI, structural MRI, IQ, gender. Some of the data provided things like the SWAN score, but not all of them did. So.
Yeah, so when you construct your features, so let's say the structural MRI, then do you construct some higher level feature, or you just give them the intensity?
So one of the things that we found is that because it was so different across sites, we actually found that it was better to train classifiers on each site independently, and then we used a neural net for learning the information across sites and making the eventual prediction. But it was just too difficult trying to find a mapping between the different sites.
So I'm just imagining, so at the beginning, if you include so many features, then if you have more features than data size, then you just have no choice. You have to use a certain type of feature selection, right?
Right. Yeah. So actually, in the Weka demo, one of the old demos that I have on the website, it actually shows that with 13, I think you start off with 13 features, and a couple of them are highly correlated, so sort of somewhat redundant. So even with 13 versus, say, 9 features, you can actually see a pretty big difference in the classification accuracy. So if you think about the brain, how many very close redundant features we must have, it really does make you wonder to me, feature selection, it's very important doing something to increase the sparsity. So, yeah. Yeah. I wouldn't mind a repeat of the question.
You want me to repeat it or her to repeat it? Okay. If you're primarily interested in not just classification accuracy, but how which brain regions or voxels are most informative for your task and figuring out the pattern of activity that allows for some task, but it's not a great practice to just interpret the weights that you get from SVM, what would you suggest using? What sort of method would you suggest using? Searchlight primarily, or?
I would say voxel-based encoding methods.
Okay.
Yeah. Or, I mean, if you're really just interested in that, maybe you just run a GLM. If you're not interested at all in prediction or prediction accuracy, because it is very difficult to. I don't know.
You're still interested in prediction accuracy, but in terms of not overall how high can your accuracy be, but specifically which regions have the most informative information?
So that's actually a really good question. I think I had a slide that I didn't keep. I wasn't sure if there would be enough time, but you can actually use, if you do it carefully, you can use encoding and decoding collaboratively. So you can do something like run a GLM analysis on the subset of your data, which is your training set. Say you get a couple of different regions of interest that you're interested in. You can do just a comparison of which one has the highest predictive accuracy to try and then determine which regions contain more class-specific information. So if you do something like visual face recognition, if the images are really similar, maybe V1 will be activated with a GLM task, but it might not actually contain that much class-specific information. That might be more IT or something like this. So that's kind of an example, but you can certainly run those separately to see which areas contain more diagnostic information. Oh yeah.
About the feature selection, I know, Torwegger used penalized regression and PCA that can do feature selection automatically, and there are some ElasticNet and other penalized regression methods that actually do a very nice job of feature selection. So I wonder if you can comment on that, or.
Yes, I mean, absolutely. You can use L1 norm, or you can use the ElasticNet, the L1, L2. That Broderson paper that I had here, they actually used an L0 norm to get a really, really sparse. So you can use different penalties to increase the sparsity. And I'm not sure which particular paper you're talking about, but if you use something like PCA, then your features are independent. So this issue of the shared covariance doesn't really become a problem. So you can actually just interpret those weights directly, I would think.
Right, I think that's pretty much what Torwegger's group did, with a little bit of penalization. But I mean, there are some papers using ElasticNet and other regularized regression approaches with different cost functions that can actually do a very nice job of feature selection.
Absolutely, yes. That's a good point. That's a really good point.
Thank you for your presentation. I think you're right in saying that we're all tempted to look at the weights and try to make something out of them. And it seems like perhaps there's no way to salvage them. But imagine that you have several classifications within the same feature space, and so you'll have different weights for each classification that you do for binary classification. Certainly doesn't get at the covariation problem, but doesn't it become, if you can plot different sets of weights for different classifications within the same set of voxels, does it minimize the problem? Can you start looking at perhaps patches of voxels that have more weight for certain classes? I mean, they all share information, so it's the same set of voxels. The information sharing is perhaps similar, but if you have different weights over different classifications, can that help somehow?
That's actually a really interesting problem. That's a really interesting point. So you're saying that if you were maybe doing something like a cross-validation, like a tenfold cross-validation, to look at the distribution of the weights, is that what you're saying, over multiple runs, say, to see if that can inform that may be an interesting approach. What I've seen is that the redundancy really is a big problem. So something that has a strong, that contains a lot of information, if it's next to another voxel, or even if it's far away from another voxel, if they're both included, and they both have class-specific information, but it's similar, then the weights for both of them is going to be decreased. And it gets worse as you have more and more redundancy. And so when you're looking at the weights, the noise, if it's just but the same thing happens with the noise as well. So if you have lots of redundant noise voxels that all can absorb this covariance in a useful way, then those weights also do decrease as well. So in that Halfa paper, when they say to take the inverse transpose, that works really nicely if you have just two features, 2 channels or something like this, or just a small number of channels. It's not going to be too much of a problem. It's when you have a lot of redundancy that you really see the weights trail off. I mean, you could just look at yeah. It's a difficult problem. How do you make sense of the feature weights? And hopefully there's some way to salvage it, but as of yet, I don't know. There's also things with that back projection when you take the inverse transpose. You're making some assumptions about the distribution of the noise in that sense. If the noise is not Gaussian, it also doesn't necessarily work.
Hi, I just had a quick question about kind of what you're using to determine or to judge the classification, and if you've ever looked at using something like the reproducibility of the weights or the stability of the weight maps, and kind of what your thoughts on are kind of incorporating that along with accuracy.
Like I said, I think that's a really interesting thing to look at is the stability. I haven't personally looked at that. I'm not sure. I'm sure somebody has looked at that in the machine learning world. But the other thing is with machine learning, in that world, most people are just interested in the prediction and the accuracy. They're less interested in this interpretation problem. That as neuroscientists, we're more interested in what's going on that makes this work. So I don't think it comes up quite as often, but I think that is a really interesting thing to look at, the stability of the weights that you both have brought up. That's a really good point.
I'm wondering how much it makes sense to interpret these weights, even if the different features are independent, in the context of machine learning being a multivariate sort of approach, and that it's really the combination of all of the different features that create good classification.
Exactly. Yeah. So you nailed it. It's the combination that produces the accuracy, and it's because of the multivariate nature that they all, if they have shared covariance, when they interact together, that's what makes it very complicated, the interpretation. So, yeah, I think you summarized it very well there, almost in a comment. That's what adds to the complexity of the interpretation, even with a linear classifier. So.
And what's happening when the features are independent that make us then able to interpret the weights?
So.
If that can be said quickly or.
Yes, yeah. So I think if you think of that geometric interpretation of that figure from alpha, if there's, this data is kind of rotated a little bit, so that rotation is the covariance. So if there's no rotation, if there's nothing shared between the two, then the weights, the way that it ends up getting assigned is that if the two are orthogonal and the dot product is 0 and everything, then this ends up not being a problem at all. You can just directly interpret the weight. So, yeah, it's this rotation which can cause the W vector to have strange assignments. So, yeah, I don't know if that helps at all.
Others? So join me in thanking Dr. Douglas for this. So our afternoon, if you look at the schedule, has time for you guys to work on debate stuff as teams, which